Perfect. All right, so glad to be talking here. We are going to talk about um, how to use foundation models or build foundation models for robots in action. And one of the key things that we'll be talking about is if we do it in a physics-informed manner, that is very important to get the physical AI to work. So a little bit about myself. I did my PhD from Stanford, worked with Andrew Ng. We built a robot that can unload items from a dishwasher. Uh, then I was a professor at Cornell University. In parallel, I started building companies. So consulted with Microsoft as a Microsoft Fellow. One of the companies went public called Catapult. And today uh, we have started TorqueAGI because we are in a world where we are exponentially moving uh, towards AI enabling a lot of things, right? So the reason uh, OpenAI ChatGPT is so powerful is because it is one AI that can solve multiple problems. So that changed as compared to what was there 10 years back. So you had to have a different AI for spam classification, some other classification, sentiment analysis, and so on and so forth. Now you can have a large model, you can prompt it in many ways, and that is one of the reasons of a big revolution that it has enabled so many applications and an entirely different way of approaching things. At TorqueAGI, we are dealing with enterprise robots. And what that means here that with enterprise robots, we are putting them in production. We are solving very interesting problems. There's one unique thing about physical world which is not there in the digital world. So in the digital world, uh, you are dealing with words and thoughts, right? You can talk about flying to the moon. Next instant, you can talk about going backwards in time. But those things are not possible to do in the physical world. So, in some sense, it's an advantage when designing physical AI, uh, and that helps us get to the finish line faster. And these are some of the types of the robots that we are working with. So we are looking at dexterous manufacturing, whether they are humanoids uh, assembling tasks in automotive factories, or they are construction robots finishing up a drywall, or there are supply chain robots that are putting a variety of things like boxes, handling your packages in these environments. So that's the scope of the applications we are looking at. And here's a quick video. So here it's a humanoid robot in an automotive factory. There are wheels over there, and it has to uh, reason about the world, find where it should walk, where is the dot box, think about, oh, I need to slide that box first before I can grab it because it has some constraints. And once it has slided like that, then it can pick it up, right? So this is a sequence of tasks that the robot must do, which basically go in the three categories: perception, reasoning, and then acting on it, reacting on it. Uh, so we are essentially building one brain that can deal with variety of robot form factors, all the way from agricultural robots to supply chain robots to different types of robots. And then this is a similar uh, unlocking that has happened in digital AI, like with ChatGPT, that now it is actually possible to build one AI that can be embodied into different robotic form factors and be made functional. Um, so one of the common themes is obviously data, right? Like how do we get data? How do we train a model? Now that's where the gap arises. So a long time back, in about 2013, when we were doing research, we said, okay, we are going to look at some very interesting tasks. Like let's get a robot to cut food in household environment. So this is a robot. It has two arms, and it has the goal is there are about 100 different food items. There are about 500 different recipes. Can we get a robot uh, to perform these tasks, right? So one thing we did is first thing is we went online and downloaded uh, billions of images, videos, and robot action data. We created some training systems, and what that allowed us to do is to train a large model. Now, this was not very large. It was only, I think, about 100 million or 200 million parameters. This was from 8 years back. But one of the exciting things that opened our eyes was, if you look at it, this is a projection of one of the inner layers of the network that different modalities, which is text, 3D shape, and images were all co-located into the same part of the space. What it means is, if you think about a cup, you say a cup, or you give it a picture of the cup, or you give a 3D model of the cup or a point cloud of the cup, it's all in the same space in the network, in the latent space. And that is really one of the reasons that the latest techniques like VLAs and others are working. And This is very powerful because now you can train the models from a variety of data. So if you have certain text data, it can help in learning new concepts. And if you have image data, that can also help. So you don't need all the data in all the formats. There are many ways to train the model. Um, and basically, we trained this model, and there are a couple of other works that have been doing that. One of my students went to Google RT2 group. We trained the model there, and this purely data-driven technique runs into a few problems. So if you look at the video, and you have shown a lot of videos of this milk being, and then you ask the robot to replicate that scenario. The problem is this behavior cloning doesn't work all the time because here the robot, in a purely data-driven manner, does not yet have the capability to reason and perform these tasks. Um, so one thing we found by doing a variety of these different works is brute force data collection is costly. So when there was this RT2 paper in about 2023, uh, if you look at, there were a dozen robots, and the task was to open this shelf, the office shelf, and every shelf is similar, every robot is similar. You just have to spend about 50 million or $100 million to collect a lot of data. And if you collect that much data, then you can clone the behavior and then you can start opening the bookshelves. So that's a challenge. That makes it infeasible. So now what happens is, if we take the same brute force approach of collecting extremely large amounts of data to train physical AI models, that the reason it worked in the space of digital AI because there was a lot of data already available. So when people started training the models, there was 20 years of data already on the internet that you can consume to train the models. That is not the case with physical AI. Now we can obviously do a few data collection by having the robots go in the world, by having videos and so on and so forth. But the gap between the data that we can collect and the data we need in a brute force approach is more than 4 or 5 orders of magnitude. And that's a very big gap. So at TorqueAGI, what we realized is the we have to capture the unique nature of physical world, which is actually physics, right? So I'll go talk about it through a illustrative example. So one of the elements of physics is kinematics. So this particular work was about tracking humans, following their gait, and so on and so forth. And here, what happens is you can take a large amount of data to learn about human gait and behaviors, and then you need millions of data points to train a model. And the point of this work was, if, as an illustrative example, if we take the human being and break it around into a graph, which is legs are separate, the arms are separate, and this is the isomorphic transformation between this graph and the models. And you are training the models. What happens is now suddenly is you have the ability to compose the models. You have broken the problem into small parts. And in a manner because humans and robots have a kinematic form factor. So by using that, again, as illustrated examples in this video, what you will see is the effect of composition, right? So here is a human on the left, which is slowly walking, and the human on the right, which is walking fast. And now if you have to if you combine these two things, the slow and fast human, the human can now you get the effect of a combined walking behavior. So what that means here is that if we start adding these physics reasoning, we can get very powerful cross embodiment and 1000x data efficiency. And some of the people in the field like Ilya, Jan LeCun, and others uh, uh, have really making the point that a LLM, the amount of training data that it requires to train a model is insanely large. A child is learning intuitive physics like object permanence, gravity, kinematics, and so on, which the current models are not doing that. So, based on this philosophy, what we have done is we have designed our loss function to be cognizant of physics. So in a typical large transformer or large scale model, you are having, for example, a cosine loss function, which is a great loss function for word vectors or tokenization, where you are taking the cosine angle between the two vectors, and that's a good loss function. But it turns out that if you are dealing with uh, physical world, a loss function which is motivated by physics is very, very powerful. So what we have done is incorporated the physics-based loss functions and physics neural operators as part of our transformer architecture. And what that does is that if we are having an industrial arm unloading boxes in a truck, those get embedded appropriately into a loss function. And if later on we want to train a humanoid on a similar task, sure, the humanoid is not the same as a industrial arm, and this automotive part is not the same as boxes. But as far as AI is concerned, if transformed through appropriate architectures, it starts to work. So we are seeing very powerful effect of that. And then because of this, uh, we have even gone ahead and worked with uh, autonomous tractors. And when you are working with autonomous tractors, there are numerous tasks you have to do. You have to figure out uh, what is a weed, what's the crop, if there's a fruit, how do I deal with dirt, and you have to perform dozens of tasks on several different robot form factors. And this approach of designing the architecture based on physics allows rapid adaptation across new tasks and new robot types. Uh, there's a little bit more digging deep into the technical architecture. The way it works is that in real time, the input is coming. You have embeddings so that it maps the different modalities all the way from touch to word vectors to 3D to trajectories, all into the same space. This physics-informed VLA model is having a loss function which is very physics motivated. The physics neural operators are helping different elements as a tool that is available, and the agents are providing interpretability. So while all the model uh, is one model embedding all different sensor modalities, all different tasks, the agents provide interpretable modular use of the model. And then obviously agents is nothing more than a set of prompts, memory, system, and so on and so forth. There's one more important part to all this. To get this to work in production, it has to work in real time. And that's a big challenge because uh, the VLA models are good at reasoning. The problem when you put them in a control loop is that they become extremely slow. So what we have done is we have achieved a 30 FPS performance by really nailing down the GPU orchestration. So the data goes into the GPU, the model lives into the GPU. This is a heavyweight 27 billion parameter model. It's optimized for GPU processes. The agents that are providing the output and flow, they are using pointers, and these are very thin agents. And that way, we can get very efficient real-time performance. Uh, and then this is what is allowing the robot to do numerous different tasks. For example, in this case, you are looking at a robot uh, closing boxes. In another case, you are looking at a robot cutting food. And this is a blunt knife. So with a blunt knife to cut a variety of food items from tomatoes to lettuce to cucumber to so many other things, it is a pretty challenging task. And the reason it is able to work through that is it is learning a mental model of basic physics. As it is manipulating the box, it is making a mental model of, oh, box has articulation. It has a few other things. And then when you that allows us to perform many tasks, including long horizon tasks. So this video is a little. Take some nothing like that. Add ice cream of your choice. Finally, add raspberry syrup to the mixture. So in this case, the person asked to make something called an affogato, which is take ice cream of your choice, add raspberry syrup, put some coffee or something else in it. So the robot is able to map and reason about, oh, I have to get coffee. So is it a coffee mug or is it a coffee dispenser? If it's a coffee dispenser, how do I uh, press the particular lever? If it's an ice cream, I need to do a scooping action. Um, and if I have to now go use the raspberry syrup, what is the motion I need to do? So it's able to sequence long horizon tasks in a thinking or a planning loop, and then execute on it through a React loop at the bottom. So it's a two-tier architecture that is being implemented here. The funny thing is, uh, this particular video, this is from about 7 years back. It took forever to get the ice cream, so ice cream had melted back then. But now we are living in a different world. The GPUs are more powerful. We can run things in real time, and this is the most surprising thing that we found. That as we implemented these techniques on, for example, this construction robot, which is doing painting, and for those of you who have ever dealt with construction or drywall, this is a very hard task to make a smooth drywall. You have to paint, you have to scrub, you have to find out the seams, and so on and so forth. And the interesting thing is to get the full production power, we had to only use about 100 examples. And the reason is it has a very strong base knowledge of the world based on internet data, public data sets, and so on and so forth. Then it has learned a reasonable model of the physics. With those two, it has to only see a few robot examples to get performant output. That is why it is able to do this for only 100 examples. Uh, so the real way to use the model that we are going forward with is that we have a general model, and we are creating specialized agents for different robots and different tasks within each robot. And this is how it looks like. So think of the model as the back end, and the agents at the front end. Agents define what you want to do. One of the reasons that this architecture is very useful than an end-to-end architecture, which we don't like, we like this interpretable modular architecture, is because it gives a product handle or interpretability to the equation. Now, human and the obstacle, for a robot, they are the same thing. Humans are obstacles your robot wants to avoid. But it turns out uh, the requirement to avoid humans is 99.999 versus uh, obstacles which you can once in a while bump. So this provides that level of interpretability. And to answer the question, yes, the model can ingest a variety of different form factors, or this is how it's working for variety of different sensors, whether it is 3D, 2D, action, trajectories are all embedded into the same model space. So as far as the model and the agents are concerned, it is very agnostic, and it can work with a variety of different sensors from 3D, 2D, audio, trajectory data, and 3D, and so on and so forth. Coming back to here, and now moving on, the way now we are programming robots is entirely changing. Earlier, for each of these boxes, you would write a traditional computer program, and you would use a one specific AI, maybe trained model. That's how it used to work. Now what is happening is, excuse me. Now what is happening is you are looking at uh, entirely new way of programming robot structures. So you have a very powerful model in the back, which is living on the edge, on the robot PC, in the GPU. And now, when you are using the model or harnessing the model, you are designing it through an agent. An agent is a set of prompts, memory, tools, and certain parameters. So you are in 80% of the cases, you are no longer writing traditional computer programs. All you're doing is saying, in this particular case, hey, and these are all pointers, so data is actually not passing through linearly. In this human agent, what it would do is that, hey, find me the human. Then the next one would say, hold that thought, track that human if it is walking through. And this behavioral agent will say, okay, well, I have found all these obstacles, humans said, blah, blah, blah. Hold that thought, now figure out a best way to proceed ahead and drive this vehicle. So this is for a driving example, tractors in a field. And this physics is what is really giving it that power for world model. So if you look at some of the examples, when you think about these boxes piled up in the back of a truck, given the noise in the sensor data, the nuances of doing a robot control, it's a very hard problem, even in that narrow space. So the model has to reason about which box is on top of the other box, what is going on, and that is what is allowing these robots to perform in practice. For example, you have criteria about how to pack these boxes in a nice way and do it in an efficient manner. So this is what a typical application looks like in this box packing space. I will show you a few more examples of how we have taken our model, distilled it for a particular application, build agents out of it. So we already talked about the box handling scenario, and this is a little bit more insight into what it is actually doing. So these agents that are there in this example of logistics space is one agent is having the robot cognizant of human in the environment. So a robot should slow down if a human is around. The second one is talking about, oh, I have found the boxes, but how are they packed up? What goes on the top of the each other, and so on and so forth. So this is now you can extend it. What we are looking at is, hey, can we take some of these models and now unlock newer use cases? Now, luggages are not boxes, but as far as AI is concerned, it's very powerful. The same architecture can now handle, and we can design a robot that can handle luggage at the airport. Uh, and these are some of the other robots that we are looking at. So one of them is a humanoid application where we are having a humanoid work in factory floors, assembling tasks, moving materials. We are having construction robots, drivable robots. So this is very exciting times because each of these jobs have 10,000 plus stations in every country, in every company. So, for example, a robot that can handle boxes, think about how many boxes are handled every day. A robot that can assemble a gearbox, think about in a large company how many gearboxes are assembled every month. So that's why it's a huge opportunity to have robot really bring a massive change. And the key to bring this massive change is the right AI. The AI that can consider data, that can work in real time, but also understand and execute with physics in mind.